The Milky Way is a tremendous structure in space containing billions of stars and trillions of planets. In their turn, these objects are surrounded by gigantic clouds of interstellar dust and scorching hot gas streams. All these components make up the bizarre and fascinating picture called galaxy. And today, we invite you on an exciting journey across it.
Its life where it's starting to die. Our Sun is no exception either. In an estimated 5.5 billion years, the Sun will exhaust its hydrogen and balloon in size, expanding to about 250 times its current diameter, while ejecting over a third of its mass. This will mean that Mercury and Venus will both be engulfed and destroyed by the giant, and while Earth may just escape this fiery ending, the planet's surface will be fried, and surface conditions will become similar to that of Venus, and will never be able to support life again. Red giants aren't the only things that can be formed in this post-production phase either. Stars with a mass several times larger than the Sun will expand so much that they are classified as supergiant stars, and stars with a mass in excess of 9 solar masses can expand to form blue supergiants before evolving into red supergiants. If the star is abnormally massive, for example much more than 9 solar masses, we tend to classify these as hypergiants. Particularly massive stars can also evolve to become what is known as a Wolf-Rayet star, which emits elements heavier than hydrogen and helium from the core due to the intense mass loss after the main sequence. The biggest known star in the galaxy is commonly attributed to the beast that is UY Scuti, a more recently classified giant of the Milky Way. Before that, it was VY Canis Majoris, which may still actually be the largest star we've ever discovered, because all of the stars estimated to be larger have much less accurate estimates of their radius. But, taking UY Scuti as an example, it is estimated to have a radius of about 1,700 solar radii. That's 1,700 times the size of the Sun, which sits at about 1.3 million kilometers in diameter. This mind-boggling size means that were you to place UY Scuti at the centre of our solar system, it would engulf every planet, asteroid and moon as far out as Saturn. To put that size in another kind of perspective, if you were to fly an aeroplane around its surface at just under 1,000 kilometers an hour, it would still take well over 1,100 years to circle it just once. Some of the biggest stars we've ever discovered have crazy numbers associated with their size, and given that this is just within the immediate vicinity of the Milky Way, you have to wonder what else could be lurking out there. As mentioned, even though these stars are awesome, they are in the dying phase of their lives. As the outer shell layers fuse hydrogen in these massive stars, the core becomes heavier and its temperature rises. When the temperature is at a high enough level, helium fusion begins violently, which is known as a helium flash. This causes the star to shrink in size very quickly, and even with some variations of the process, all red giant cores eventually become degenerate as the star begins to die, entering the final fantastic phase of its life. After a star's core becomes degenerate, it starts to shrink. The radiation from the surface increases dramatically, creating pressure on the outer shell, which in turn strips back the outer shell layers. Depending on the mass of the star in question, a number of very different outcomes can then occur. If what is left of the stripped back star is now less than 1.5 solar masses, then the star will shrink to a size comparable to the Earth and will become a white dwarf. White dwarfs are not heavy enough for gravity to continue compressing them, and the electron matter inside the star is no longer in plasma state. Eventually, white dwarfs burn themselves out, emitting no more light or heat, and enter a theoretical stage known as a black dwarf, or a cold star. The lightest stars end their lives fairly tamely. After they have finished their main sequence, they become far smaller, and from there they just fade away. When it comes to more massive stars, these can start to produce iron in their cores by fusing helium into heavier elements. If the iron core is above 1.5 solar masses, then the shrinking and receding star will no longer be able to support its own mass. It will begin fusing heavier elements, iron, nickel and cobalt, and this will mark the final moments before a fantastic death. No heavier elements can be fused, and so no new radiation is produced to counterbalance the gravity of the core keeping the star intact. The star can no longer keep itself hot enough, and electrons will be driven into protons, forming neutrons, neutrinos and gamma rays, causing the star to violently implode. This collapse causes a shockwave, which causes the outer layers of the star to blow up in a brilliant explosion known as a supernova. Supernovae are among some of the brightest things in the universe. Sometimes they are so bright that they even outshine their entire galaxy. The explosion disperses the star's outer layers, leaving a remnant in the surrounding area. These remnants are called nebulae. One such stellar ghost is the Crab Nebula. In fact, this is exactly what is predicted to happen to a nearby supergiant star in the Milky Way very soon. Betelgeuse is an extremely luminous red supergiant star over 900 times larger than the Sun, located 640 light years away from Earth. It is one of the 10 brightest visible stars in the night sky, and is highly unstable and beginning to shed its outer layers. When it finally enters the ion fusing process and implodes, it will go supernova and its brightness will rise to billions of times brighter than our Sun. Documented cases of supernova explosions have only happened a few times throughout history, and none have been as close to us as Betelgeuse is. So, when it finally does blow its banks, the resulting brightness will be visible from Earth during the daytime and the nighttime, with some predicting that it will even outshine the Moon for the best part of a year. Given that the light delay is over 600 years, it could have already happened and the light is travelling towards us now, so there's a slim chance that you or I watching this video may be able to witness Betelgeuse go supernova and outshine the rest of the galaxy in our lifetimes. As for when it will happen, well, we simply cannot tell. After the brilliant visual display of the supernova has occurred, the cores of these stars can still continue to evolve. In some cases, the core will collapse in on itself and form a very dense, comparatively minuscule object with an immense gravitational field relative to its size, known as a neutron star. What was once a massive star capable of engulfing millions of kilometers collapses in on itself to form an object no more than 30 kilometers wide. In some cases, these celestial bodies will rotate rapidly and sometimes emit beams of radiation detectable from the Earth, called pulsars. It was through this phenomenon that in 1967 a signal named LGM1 was discovered, a radio signal from a pulsar that was initially attributed to a transmission from an alien civilization. Most neutron stars have such strong gravity fields that, were you to drop a teaspoon from shoulder height to the ground while standing on one, the spoon would reach speeds in excess of 22,000 km per hour before it collided with the ground. However, that still isn't the most extreme thing massive dying stars can form. Not all post-supernova stars collapse to form a dense neutron star, some take it a step further. If the stripped-back core in question is in excess of 4 times the mass of the Sun, then the resulting force of the implosion will be so great that it will compress the entire core into a single microscopic point with near infinite density, known as a singularity. The resulting gravity field is so strong that, past a certain point, not even light can escape. The massive collapsing star has now formed a black hole. Black holes are some of the strangest things in the universe, and are the ultimate all-consuming eventuality for the most massive stars. While these black holes aren't usually the supermassive black holes at the centres of galaxies, they can still achieve some pretty impressive sizes. Whatever happens to a star when it dies, it's never usually boring. So there you have it. We've now covered the life cycle of a star, from its formation to its death. These massive thermonuclear explosions are responsible for shaping so much of the universe you see around you, where galaxies are the legions of the cosmos, stars are the centurions. But the question is there a size limit that stars cannot exceed? Well, theoretically yes, there should be a size limit for stars, and this is not due to the mechanics of the star itself, but is more to do with the star-forming molecular clouds. These clouds cannot exceed a certain mass when incubating stars, or they would lose their star-forming properties. So, with this in mind, some papers have speculated that the upper bound for stars should be about 150 solar masses. But then again, we've discovered stars, such as the blue hypergiant Pistol star, which are estimated to be closer to 200 solar masses. So no one really knows for sure. Ultimately, we can conclude on an upper bound limit for mass, but when it comes to size, there are a few more variable factors. The largest known star is about 1,700 times the diameter of the Sun, and some predict that cool supergiant stars could grow to as big as 2,600 times the Sun's size, but others dispute this. Principally, there is no absolute cutoff point that we can set the benchmark at because we simply don't know enough about the detailed long-term process of star formation and evolution. And who's to say that in the future an abnormal star won't be formed which is greater than any other star that has ever existed? The idea of an upper size limit hinges on the assumption that the number isn't fluid, but we simply don't know. And even a survey sample of an entire galaxy doesn't really provide the clear picture we need to gauge a better understanding of star metrics. However, every discovery we make challenges old ideas, and so the only way we can ever conclude on star size limits is to continue to discover, observe and research these giants of creation. Stars are truly some of the most wonderful things in the universe. With our wealth of knowledge now, it's easy to lose sight of them as we think bigger, galaxies, galaxy clusters and the rest of the universe. But when you break a galaxy down to its key component, you see the root cause of so many defining features of our universe. All because gravity attracts hydrogen and helium atoms together, and given enough time, complex processes produce these brilliant stellar firework displays. From the dwarfs right up to the hypergiants, each star has its own story to tell, its own solar system, and its own possibilities for supporting life. And with 300 sextillion stars out there, and hundreds of sextillions more beyond the boundary of the observable universe, the possibilities really are endless.
And whenever some of them are solved, they add to our knowledge about the universe around us. Are we to solve all its mysteries someday? Time will show.